So, how skilled engineers and developers write efficient and fast codes for tech companies and startups, even in the era of AI code assistants that can help them. Hey everyone, in this episode I'm going to present some secrets and strategies for high and efficient code development and productivity. These strategies and secrets will form some tips for us to unleash our knowledge, skills, and use them in the best way and have very efficient end code. I will share 5 tips that can make all of us write very efficient and fast code for tech applications in machine learning, artificial intelligence, and also for scientific computing like physics, chemistry, but also automotive simulations. Those tips will be drawn from my personal experience, but also from the work of others and working with others in the tech environment, in our startup, in universities, but also in many other communities. Some would think that AI can design and write codes in full for us, but this is not ultimately true. Things like architecture design, but also code workflow, testing, and even making sure that we get the correct results, this is something that not all the time AI can help us with. If you are not a professional programmer already, I really disrecommend using AI in the beginning. This is really will kill your creativity. Think about this. If you are a manager in a company and you try to direct and, for example, give advices to new employees, if you have done part of their tasks, you have the problem-solving skills built in your muscles and in your brain. So you can direct them and in solving problems and lead them in a much better way. But if you don't, you will find hard times in doing so. So this is similar to the code. If you get your hands dirty and you try to think about the solutions yourselves, you sort of build this in your brain and your muscle memory. And then later when you use, for example, AI for simple tasks, you know how to control the AI assistant routines to help you in a better way, but not to have the way around, that AI controls you in the solution and you don't know how to have a control over your own piece of software. So tip number 1, we need to think strategically about our code. What we want to achieve from this piece of code. What kind of expected results? What could be our inputs, but also the expected outputs of this code? If you do write code for machine learning or tech simulations, like a simulation for a car, chemistry, physics, and others in high-tech, you often use algorithms behind the design. These algorithms are a set of mathematical rules of equations, for example, that take a specific input or inputs and produce it to be outputs. So you need first to make sure that the algorithm is written clearly in a way that is easy to be converted into code. Now, this is interesting by itself. If you don't know how to write algorithms that could be easily converted into code, we can just discuss this in a separate episode. Typically, this involves writing algorithms in a way that understood by a computer, and either it could be, for example, vectors or some element-wise operations or matrices. But we will talk about in future episodes. So by starting designing our codes visually using flowchart, that will solidify our thoughts and we will know for sure what we are going to achieve from this code. So hence putting things visually will help us having a good mind about what we wanted to achieve and also clear path to the results. So now we are in tip number 2. We need to try to identify the common routines or tasks in the code. So we need to think of our codes like building blocks. We need to ask ourselves what kind of those blocks will be used frequently throughout the code. Can we isolate those common blocks and separate them from the rest of tasks? So with this approach, you can isolate the frequently used code blocks and in libraries and load them whenever needed in the code. And also you might store them on the shelf for future projects. And this means that you need to develop them separately, check them separately, and keep them on the shelf. And also that will help you that you have some blocks that you have in your own that you can recycle and use for your future projects. Also, you might think about what kind of some already out-of-the-box libraries that you can use. And also, might help you in knowing also what you can use out of the box to help you in your code. For example, think about the common tasks that, for example, use in your code, like calling a specific algorithm to do, for example, fitting of a function or to evaluate some coefficients for machine learning. And you might use this out of the box, out of other, for example, open source libraries or packages that you can load in your own programming language environments like Python or Julia. So you can call those whenever they are needed, and you know that those parts you don't need to develop them yourself. Just you need to know how to use them from other packages and libraries. More importantly, will save us time in debugging. Quite often, if we isolate those tasks, we call them routines. We check them first, so we know that those are correct. They produce the correct results. So whenever we are debugging the code, there is no need to go back and forth through the entire code in debugging. We know that those common blocks are correct and they have their own separate testing. So we focus in identifying the issues most of the time on the rest of the code. And even if you find a bug, it's easy to fix it in this common routine, and instead of fixing it in the entire code. So like copying, pasting those routines during the entire code, you might fix it in one place and not in every place. So you might end up having this bug multiplied by the number of the times that you have copied, scaled exponentially with the other parts in your code. So by isolating those in a separate library, that means that you can just fix this library, and whenever it's loaded, this bug is solved or fixed automatically. Tip number 3, represent your piece of code using software diagrams like unified modeling language diagrams, for example, to have a better idea about the building blocks used in your code. So this is similar to making stories. You often need to combine blocks of the story and make a timeline of them. Code is similar. We need to represent the building blocks or routines of our code visually using code diagrams like unified modeling languages. With that, we will be able to group, for example, certain routines. With this approach, we will know which kind of tasks could be grouped or combined together. This is similar in making a story where certain events and timelines are combined together in sort of story blocks, like a chapter or a scene, and code is similar. We need to represent the building blocks or routines of our code visually using these code diagrams, and with that we will be able to group certain routines together in a specific order, or for example to make a larger routine that can perform certain tasks or computations. That will help us in testing and debugging, but also to design test units whenever we need. With this approach, it will be easy to see what kind of routines or tasks that can be combined together to perform some larger tasks, for example, and to know the specific order of those tasks in these larger routines. Tip number 4, we need to divide the code into modules or jobs or some group routines. So now at this stage we have our own design. We know the plateau of our code. At this stage we know how to group things together and take some decisions based on those things. For example, some programming languages can do this task, like object-oriented languages. And we can do, for example, this in Python, for example, like a class that combines functions that can perform certain group of tasks, and that class will perform one particular action that depend on those, or a cluster of actions. So now we have our own design of the code. We have the full plateau of the code. We know what kind of things we can group together to perform larger tasks, for example, or a task that's composed of small tasks that are coupled or connected in a specific order. So we might think in object-oriented programming in that sense. For example, some programming languages can do this for us. For example, we can do this in Python if we develop a class of some functions, and every function has a specific small tasks, and the entire class is dedicated to perform a collection of tasks or one larger task, for example. If we use Julia, for example, we might think of modules, and the module can combine several functions and structures and so on under the module. And this module could be dedicated to specific class of actions, for example, or tasks. Similarly, modern Fortran, we can think about similar approach. But now, at this point, we have really to stop, and we need to start to make a mock or a dummy code in which we test our approach. So let's pretend that we have everything, and we just start programming and writing our dummy script or logical design. So let's have a look on the following. I'm now developing a mock script in Julia. I will make a module, for example, called module quadrature. I will make a class called quadrature, and this class will have several functions. Every function will generate a specific number of points that correspond to a different quadrature methods and weights. So for example, I can make a function called quadrature, Legendre quadratures, and that takes the number of points in, and then I imagine what kind of output I need. I need from this function to have the points, but also the weights. The idea of quadrature is that if you choose a specific method that corresponds to a specific function, you might evaluate a mathematical function on these points and multiply this evaluation of the function times a corresponding weight. And if we sum, sort of like we are making integration of the function on this specific points without the need to evaluate the function numerically on a very large grid. So by making this dummy script, we are sort of asserting the initial visual design, and we will know if this is correct or not, for example. If not, we might need to step back and do some corrections. We also can get a better idea about the type of variables and the data we are using, and the input and the outputs of everything. By writing this dummy script, we are sort of asserting our initial visual design. Is it correct? Is this matching what we thought about? If not, we might take a step back and go and correct our design. For example, adding a certain task or clarify thing about a specific task and so on. So the beauty about writing dummy scripts, it gives us an idea about what actual implementation could be in a very, very short time, and what kind also of variables, input data, and also outputs we will involve in writing our codes. So once we have our dummy script, we know what we actually need to develop ourselves for sure, and what we can use out of the box of other libraries that are around us, or that we can call from built-in functions inside the environment that we are developing. It could be Julia, Python, MATLAB, and so on. But also out of the box codes or libraries could be the ones that exist on the shelf, for example, in your team or in your company, or in your repository of your team, for example. Sometimes it could be built-in packages that we load, or open source software that we are using after checking and making sure that it has a proper license that matches the code that we are developing. Tip number 5. Test the function or modules while you are programming them. I will not say this is the most important thing of all of them, but this is really a crucial tip during code development, especially if you develop a code for simulations that involves some evaluating of numerics out of certain mathematical equations and so on. So you need to make continuously that while you are progressing in your code, that you are making continuous testing for each part of it and making sure that you get the correct results. So you can solve the problem on the spot, especially for those common routines, because those ones could be your building blocks for life in many codes. Like if you develop something for numerical analysis, it's high likely that you will stick with those libraries for a very long time. So having a continuous testing will speed up the progress in development, and it will save you time in the overall debugging of the code. You can also to make unit tests in the beginning of every module. So when they are loaded into your program for the first time, there is sort of some checks, some could be some numerical evaluations or getting some numbers that you can check that the module is working properly, especially when module versions change. And this is something that I've been practicing even with our team in, for example, startups and in university and some other places where you really we need to check the code in the beginning and make sure that this piece of code generates the expected results every time. And if not, it means that either something is not loaded properly or something that has been changed. But then you will not discover this at a later stage. You will discover it in the beginning immediately when you, or for example, the user that's using the code is loading this piece of code or software for the first time. Typically, what I personally like about tutorials, for example, like for web development or anything, when the developer shows what kind of pages we need, when they set the environment, what kind of pages we need to include, for what good, for what action. So with that sense, if I cannot reproduce the developer's result, I can know for sure what this specific library will do in this specific page. So I can, for example, Google it or develop it on my own and so on. So that's very crucial to know in advance. So having said that, it really helps to know the strategy of the code, what we expect from this piece of code, what kind of results we want to achieve. And then we put everything on a paper in a sort of flow chart, what we wanted to achieve visually, and also to ask ourselves, do we miss something? Do we need to have an algorithm for a specific task? If so, do we have all of these algorithms on our hand? If yes, and all of this checklist is passed correctly, we go to having this UMLs or Unified Modeling Language diagrams. And with that, we are sort of imagining what we are going to develop. And we can, for example, think in grouping things, having modules or classes that combines small tasks or routines in bigger routines. And passing that, we go to the very important step, which is making a dummy script. We don't really fill the function, the content of the function. We just write the functions and also classes or what we imagine in our code as if we are really developing them. So we can have a better idea about what we are going to develop, but also about the inputs and the outputs, the variables and the type of data that we are dealing with in the code, and what format we need these data in, and also if we need to develop everything on our own, or we can borrow something from the shelf, like something out of the box in our old, for example, from our old projects. Can we use these things? Can we use something from our team's repository, or can we use, for example, from the built-in packages in the language itself, or from another open source software, or open source codes on GitHub or GitLab or similar platforms, and so on. And after that, we started developing and making sure that we are making tests continuously while we are progressing in developing the code. With that, we can have very efficient and very fast development of a code in less time. So at least we can have working code in a very short time. And also we can optimize it without getting into too much of debugging issues or anything. So we focus on the core tasks. So thanks for watching this video. If you like it, please do like and subscribe, and write what you think on the video below. This is not an official guide for code development. This is sort of a quick recipe of tips and best practices that can help you and us in writing efficient and fast, very good piece of code. So if you have more tips, questions, thoughts, or comments, please feel free to share them below the video, and then we are going to discuss them in the future episodes. Also, in future episodes, we are going to discuss and develop together some applications that involve machine learning and artificial intelligence for example, physics, chemistry, quantum computing, and so on. So stay tuned. Bye.